Okay, please, Benjamin, go ahead. Thank you.
Good afternoon, everyone. My name is Ben Fernando. I'm a postdoc at Johns Hopkins University in the United States. And here I'm going to talk to you about perhaps one of the more unusual events that we'll be discussing in this meeting, but I think is an excellent case study of how seismic and acoustic data, in particular data from the IMS, can help us address stories that are perhaps not all they seem to be, but nonetheless attract enormous amounts of public attention. So this story is going to start back in 2014 when there was a meteor, so a bolide, that entered the atmosphere off the coast of Papua New Guinea, so out in the open Pacific Ocean. And that was fine. No one really noticed or did anything about it for about 6 or 7 years. But then during the pandemic, a group from Harvard University decided that the signatures associated with this meteor indicated it was interstellar, so meaning that it had come from outside our solar system. And that's possible. We know that there are interstellar objects which occasionally enter our solar system. One is coming towards Earth right now. It's probably not aliens, don't worry. But they had claimed that this interstellar meteor wasn't actually a meteor at all. It was a piece of alien space debris. And they had mounted an expedition to go down to the bottom of the Pacific Ocean, where they had used a magnetic sled, so that's what you see there, to collect up small magnetic particles from the bottom of the seafloor and brought them back to the surface, and they said this was proof that an alien spacecraft had crash-landed in the Pacific Ocean in 2014. Now, you're probably thinking, like, why would you even bother engaging with this? This is clearly crazy. But the unfortunate truth is that in a media world where seismic acoustic data are perhaps not as well understood as we would like, this story got a huge amount of traction, and we saw it being reported in media around the world that we had evidence of an alien spacecraft arriving on Earth. And, you know, that's perhaps a story that we should pay attention to, given that the proof for the alien spacecraft came from no other source than seismic and acoustic data. So I'm thinking, oh gosh, bolide events, that's what I work on, except this one wasn't a bolide, it was an alien spacecraft. So let's take a look and see what we can find. You're allowed to laugh if you want, by the way. This is meant to be a slightly lighthearted presentation. Okay, so what was the model? How did this happen? So this meteor had entered the atmosphere, but of course, you know, as bolide enters the atmosphere, it's going very fast. If something does survive, those fragments are going to be strewn over many hundreds, if not thousands of square miles. Well, this group had claimed that the fireball had produced a sonic boom, which is fine, that happens all the time, but they had detected this sonic boom at a station in Papua New Guinea. Okay, believable so far. The seismogram that they purported to use in this analysis is shown in the bottom panel, and it's actually plotted as a histogram, which is clearly something only a physicist would do with a seismogram. But it looks perhaps different to many of the infrasound signatures of bolide explosions that we've seen in previous talks in this session and earlier today. So their model was that this meteor had exploded. They'd seen the direct air waves, so that's the top arrow, and then they'd seen some indirect air waves that had reflected off the surface of the ocean. And the question that we had was, okay, well, is this a reasonable model for detecting seismoacoustic energy? Is that a reasonable coupling model? And can you indeed use this one station to locate the source to a box that they'd found, which was about 100 meters by 100 meters, pretty small? You know, if IMS IDC could do that, I'd be pretty happy with it. Can we locate down to that region? And then, you know, is it true that the material that they recovered from the seafloor might indeed be bits of an alien spacecraft? So that's the signal that we were working with. The story involves sort of 3 seismometers, one IU station and then 2 from OSPAS, so really great that this is all open source data, and then 3 stations from the IMS, so big thanks to Pierre Miale for his help in being able to work with and identify those. So that's the setting. You can see the pink arrow there, which is the inferred trajectory of the meteor. That's from optical observations, and then the places where they went looking for the spacecraft are around those 2 green crosses. So let's take a look at a bit of a seismic analysis of this event. So what you're looking at here is the ground velocity over time. You'll see that the fireball is the dashed green line, and then the arrival time that this Harvard group had picked for an acoustic wave is the dashed purple line, so just after 1710 UTC on January 8th, 2014. And so, okay, there's clearly a signal there. There's something that's worth investigating. There's clearly also another signal there that started a few minutes beforehand, but they'd said that didn't match the arrival times for the distance to the station. It's about 100 or so kilometers. So let's focus on the second signal. So this signal had been taken and it had been spun as a story that from that single seismogram you can locate the alien spacecraft. So the first thing we did is we look at how many of these signals there are over the course of a day. And this is kind of a classic statistical tool to try and differentiate natural signals from artificial signals. So we know that natural phenomena, earthquakes, meteors, etc., don't really care what time of day it is. And I'm not 100% sure, but I'm imagining that aliens wouldn't mind too much either what time of day it is, right? If they've come to all the trouble to reach Earth and they've spent so long traveling, they probably don't mind if it takes an extra 12 hours. You know, they have to wait. So we see that these signals show a pattern where there's lots of them, but they're clearly concentrated at certain times of day. That is between about 6 o'clock in the morning local time and about 9 o'clock at night local time. And to me, that's a key indicator of an anthropogenic source, and probably a source that's associated with some form of, industrial or transport activity. It's peaking during working hours. And there are many such signals which, show similar kind of waveforms, even in the 10 to 20 minutes leading up to the event. So what if we look at the polarization of the signal over time? So that's the same record that I showed you a couple of slides ago. The fireball is at roughly time equals 0. We see one pulse, and then we see another pulse. And if we look at the azimuth that those signals are coming from, we see something that starts kind of down at the south, and then it's sort of trending slowly northward over time. Then there's a break of a few minutes where there's really not a particularly good SNR, and then the signal basically reverses and goes back in the other direction. So again, this is a very good indication this is probably a local source, because even at the speed of a meteor, to be sweeping across 180 degrees of source azimuth in 100 seconds would require it to be going not just fast, but like ridiculously fast. So we're thinking this is a local source, but what more can we learn about it? So this is obviously a challenge. We have a single station, but what we did is we looked at, what features on the ground might match a polarization of a source that's moving in this way. So this is a map of the station. It's the Osprey Station on Manus Island in Papua New Guinea, and it's just at the edge of a naval base. So there's a hospital there. You see the naval base up on the right-hand side, and all sorts of other things. So we're looking for a feature that might be indicative of a source that would start at a sort of southerly, maybe southwesterly azimuth, and then trend slowly north over time. And if you match up the polarization of the signal that we see, it's almost an exact match for this road, which leads from a highway up to the gate of the hospital and on into the naval base. So the signal, which had been published apparently through peer review as a signal associated with an interstellar meteor, was in fact most likely the signal associated with a truck or lorry turning off the main highway, driving up to the hospital, waiting there for a couple of minutes before turning around and driving back the other way. So, we got a media interview about this, and they said, well, was the truck in the Milky Way? And I said, no, and then I thought about it for a second. I was like, well, actually, yes. It is indeed in the galaxy. So what more can we do, right? The seismic signal with only a single station, as much as I like to do seismic data analysis from Mars, it's very difficult to say a huge amount with just one station. But the wonderful thing about IMS and the sensitivity of the infrasound sensors is this particular meteor was picked up on 3 separate sensors across all of Australia, and then there's one on Palau, IS-39. And those 3 sensors did, in fact, pick up the infrasound from the meteor. It was a real meteor. It just wasn't what they had picked up on the sensor. The sensor picked up the truck. The meteor generated infrasound. They just didn't look for it. And the azimuth, the fit location that we get from the IDC data gives us a source location that's about 200 kilometers away from where they went looking for fragments of this alien spacecraft. So for better or for worse, they did go down to the bottom of the seafloor and find some stuff. And they picked it up, but unfortunately they were looking a couple of 100 miles away from where they should have been if they thought there was any real chance of stuff from this meteor surviving. So we can go one better as well. So this great analysis that we have using IMS data, we can actually go looking for a control sample to show that similar samples, right, small metallic fragments, had been collected from the seafloor in the location of where the IMS-informed source was before the meteor had even happened. And you might be thinking, well, the meteor happened in 2014. How are you going to find samples from before then, right? It's a little weird. But it turns out that the first deep-sea oceanographic expedition ever, in 1876, actually went and sampled this area of the Pacific Ocean to try and understand what the composition of the seafloor was like. So the source location that we have using the IMS data is actually very, very close to where the HMS Challenger made some of the first ever sort of deep-sea sampling methods and expeditions in the 1870s. And we have a student now who's been working on some of these metallic fragments that we identified from the 1876 samples, which show a very similar composition to the supposed alien debris from 2014. And I think it's like a wonderful example of how seismoacoustic science enabled by IMS is linking back to this historical collection. We've been able to use a signal from 2014, processed using 2025 technology, to go back and look at samples from the 1870s, which are unsurprisingly supporting the idea that there's a lot of metallic stuff at the bottom of the ocean, and most of it probably isn't aliens. So I hope that's been a relatively engaging interlude into how we can sometimes use science to answer what we're not sure why this is even a question in the media, but is something which has attracted a huge amount of attention, and has probably brought the IMS to the knowledge of people who otherwise would not have engaged with it at all. As I always say, when both the Washington Post and the Daily Mail are on your side, you've probably done something good that day. Not what I was expecting to be some of my more impactful seismoacoustic analysis. But I hope that's been sort of an interesting interlude to you. On the next slide, the conclusions, I'll have a QR code which you're welcome to scan as well. And that will take you to a link to the published paper and some of the data sets. So thank you so much. And just remember, it's probably not aliens.
Thank you, Ben. Really interesting. Well, we know that there are not aliens then. Any question from the audience? Me? Okay, so thank you, Ben. We are a little bit behind schedule, so let's move forward to the next one.